the previous module, we were talking about examples. We have done examples related to non-degenerate perturbation theory, and we did few problems. We will continue doing some problems also, one or two problems in this module also, and thereafter I will talk about degenerate perturbation theory. I said you why degenerate perturbation theory and non-degenerate perturbation theory is different, because the relationship for the first order correction to the wave function has a summation term, and in the summation term in the denominator you have E1 minus EM naught, E1 naught minus EM naught, and that E1 minus EM naught cannot be equal, because if it will be equal then the perturbation term will be very high, and this will if they are equal, then you cannot get the psi n1 correction to the first order correction to the wave function. So what is required is that you must have a new theory for the degenerate perturbation, degenerate state, and so that way I said you called degenerate perturbation theory. Okay, but before that, let's see particle in one dimension perturbation to particle in one dimensional box we have done, and then we did the perturbation on a hydrogen atom. No, I don't think hydrogen atom we did not do. We talked about particle in a one-dimensional box placed in an electric field. We talked about that a constant potential is applied to the half of the length of the box, and then a potential, a perturbation which is not constant, is applied throughout the length of the box. Then how to calculate the perturbation? And I've given you a shortcut method also, which is applied when the perturbation is constant and when the box is unsymmetrical box. Okay, so that was the last module, and in this module again you see one of the problem is that if a particle is moving in a circular path in a plane represented by psi m phi is equal to 1 by root 2 pi exponential I m phi. If you remember, when we did rigid rotor, then in rigid rotor after the separation of variables we got two different equations. One was phi equations, another was theta equations, and we solved the phi equations and we got this solution that phi that there I have written capital phi depending on small phi was 1 by root 2 pi exponential plus minus I m phi was the solution. Okay, so and this was the normalization constant which we determined. Okay, so since it's a particle moving in a plane, and in a plane you have the phi angle only, so this particle is represented by this wave function 1 by root 2 pi exponential I m phi, where m is 0, plus minus 1, plus minus 2, plus minus 3, is subjected to a perturbation of h prime p cos phi, where p is a constant. Then the question is, what will be the first order correction to the mth state energy? So what you have to calculate? You have to calculate you have to calculate En1 you have to calculate, and for this En1 you have the formula is psi n naught perturbation operator perturbation and then psi n naught deta. So this psi n naught is already given to you, 1 by root 2 pi exponential I m phi. Perturbation is given to you, it's p cos phi. So this is the formula, the formula is already there. So if you put these values in En1 relationship, what you get is here. Now see, the variable is phi, and the phi variable varies from 0 to 2 pi, so the limit of the integral will be 0 to 2 pi. Okay, and 1 by root 2 pi exponential minus I m phi, then p cos phi is the perturbation, 1 by root 2 pi exponential minus I m phi, because you see I have written psi n naught and psi n naught. If the wave function is real, that's fine, psi n naught, psi n naught. If the wave function is not real, you can say psi n naught and then its complex conjugate psi n naught complex conjugate. Okay, so this you will have to always remember that it depends upon the wave function, whether it is real or imaginary. If it is imaginary, then the second wave function will be complex conjugate. So the complex conjugate of this should be plus I m phi, this should be plus I m phi, this is minus I m phi. Okay, so because the complex conjugate I have to take in one case and correct it. No, it's fine. Okay, so if you take this solve this integral, 1 by root 2 pi and 1 by root 2 pi you can bring outside, so it will be 1 by 2 pi, and then exponential plus I am phi, exponential minus I am phi, you will sum it up and it will be exponential 0, that will be equal to 1. So the integral will be like this one. And p is also a constant, it's written p is a constant, so p also you can bring outside, and you have exponential 0 cos phi d phi, and you know cos phi d phi you can, it will be equal to sin phi, so varies from 0 to 2 pi, and sin 2 pi is also 0, sin 0 is also 0, so upper and lower limit both are 0, and there is no correction to the first order. So this kind of perturbation to a circularly moving particle will not change its energy. Energy of the unperturbed system and energy of the perturbed system will remain same even if you apply a perturbation. So that also may arise with you in certain cases. Okay, it's not always so that the perturbation will be very small, but it will always be there. In this particular example, you see that if En1 is 0, the total energy En1 will be En naught plus En1, and it will be same energy, whatever is the energy. Okay, so En will be En naught plus 0, and it is En naught. Okay, so the energy of the unperturbed system and energy of the perturbed system are equal because the correction to the energy is 0. Okay, and it's very obvious from the calculation that correction to the energy will be 0. The only correction here in the typing error, copy and paste error, you make it plus 1, plus I am phi. So that E plus I am phi minus I am phi will become E raised to the power 0. Okay. So this is another problem, but apart from the particle in a one-dimensional box. Particle in a one-dimensional box you have done, but beyond particle in a one-dimensional box, now it's a particle moving in a circular path with a perturbation p cos phi, where p is a constant. Okay, so this then we can think of another problem. Like this is what is another problem. First order correction to energy of simple harmonic oscillator with potential energy V is equal to 1 by 2 kx square plus gamma divided by 6x cube plus beta divided by 24x raised to the power 4. Okay. Similar problem you will get in quantum chemistry by Mercury also. If any one of you interested, you can see the quantum chemistry of Mercury. It's a very good book for quantum chemistry. So this is what, if you remember, we have done simple harmonic oscillator, and where we have taken the potential energy is equal to 1 by 2 kx square. So this term remains in the unperturbed system, but these two are the additional terms which is called perturbation. So perturbation is actually gamma divided by 6x cube plus beta b divided by 24x raised to the power 4. So this is what is called perturbation. Nothing else. So if you remember what is the eigenfunction for simple harmonic oscillator, then you can again use the same equation which we used earlier, psi n naught h prime psi n naught theta, and you can calculate the change in the potential energy. So this equation you will use, and for this the wave function is beta divided by pi raised to the power 1 by 4 exponential minus beta x square divided by 2. This we have derived by the two methods, if you remember, in the earlier modules, that we power series method we used, and we also use the ladder operator method. From both the method we derive this particular equation. So this is the wave function for unperturbed system. This is the correction to the first order of the perturbed system, and if you put these values psi n naught, then the perturbation is gamma divided by 6x cube psi n naught dx plus gamma psi n naught beta divided by 24 x raised to the power 4 psi n naught dx. And in the case of simple harmonic oscillator, I talked about in details that if you have an odd value, then odd integrals are going to be 0. So this first integral will become 0, and so this first integral becomes 0, and you have only this integral to be solved, psi n naught beta b divided by 24x raised to the power 4 psi n naught dx. Okay. So if you solve this integral, you have this integral, and this integral if you solve, what do you get? So you need to put the value of psi n naught at the two places, and here you do not have any I, so there will not be any complex conjugate sort of thing. It's a real function. So here you will put beta divided by pi raised to 1 by 4 exponential minus beta x square divided by 2, and here also you will put the same value, and it will be like this one. Okay. So the first function psi n naught, then the perturbation which remains, because one of the perturbation term will give you zero integral, and another psi n naught. So three parts are there: psi n naught, h prime, and psi n naught. Okay. Beta. So what you can do, beta by pi and beta by pi you can bring outside. So it will be, and exponential minus beta x square divided by 2, exponential minus beta x square divided by 2. If you bring on the power will get summed up, and it will be minus exponential minus beta x square. So what you get is, this you bring outside, then this b divided by 24 is also a constant, so bring b divided by 24 outside, and now you have exponential minus beta x square divided by 2 x raised to the power 4 exponential minus beta x square divided by 2 into dx. Okay, and if you sum these two exponential values, then this is what is the equation: x raised to the power 4 exponential minus beta x square dx. This integral again will be from minus infinity to plus infinity, and this integral is known, and we have done in the previous modules. And if we have not done, go and see look for the standard integral table, and what you will get is 1 over beta raised to the power 5 by 2 3 root pi divided by 4. Okay, because I have used many times a standard integral, so here I have not given a standard integral. You can go and see the standard integral table, you will get it. Okay, so if you put these values, what do you get? The value which you get is b divided by 32 beta square. So this is your first order correction to the simple harmonic oscillator. En1 is b divided by 32 beta square. So altogether we did 5-6 problems based on non-degenerate perturbation theory, and this is the most common problem which is asked in your exams. If you want to do more problems, you go and see the in any quantum chemistry book. ZTLE have many problems based on the perturbation theory, so you can go for ZTLE and you can do the problems there. There are many solved problems are also there. Okay, and I said you when I was finishing this theory of non-degenerate perturbation before doing the problems, that this is applicable only in case of non-degenerate energy states. Okay, and so the next what we will be doing is the degenerate perturbation theory. If you have the same energy state but different wave functions, and for that system, how do we deal if a perturbation is made? Okay, if a perturbation is done. So what does it mean? Degenerate perturbation theory means if you have for the same En naught, you can have 2, 3, 4 different values of wave functions. It could be psi 1, it could be psi 2, it could be psi 3. I gave you the example in the first two slides that degenerate perturbation theory means energy state is same, but the eigenvalue is different. Eigenfunction is different. And if eigenfunction is different, means each of these functions represents different quantum state with the same energy. Okay, so what we say is that here in this case, we can take a linear combination of the wave functions for this relationship. So a linear combination of degenerate wave function is taken as the unperturbed wave function. Okay, instead of taking only one wave function psi n naught in the previous non-degenerate perturbation theory, we have taken psi n naught as the unperturbed system wave functions. Now here we will not take psi n naught, we will take a linear combination of these wave functions which corresponds to the same energy state. So if you have En naught is the energy, and just for the simplification, suppose that it is two-fold degenerate. Two-fold degenerate means it will have two different wave functions representing this particular energy state. So if it is psi n, these two energy states I have represented as psi n naught and psi l naught. So in the relationship of the first order perturbation, which we derived as equation 7 in the previous module, you go and see, what we will do, we will replace this psi n naught value with a linear combination of psi n naught and psi l naught, and we can write a linear combination like Cn psi n naught and Cl psi L naught, and we will replace this, we will use this wave functions, a linear combination, into this equation. This is the equation for first order correction to the perturbation. Okay, if you remember, we expanded the psi n value and En value, and then we got this, we equated the coefficients of lambda raised to the power 0 gave you zeroth order perturbation, then lambda raised to the power 1 gave you first order perturbation, lambda raised to the power 2 gave you second order perturbation. So it is that relationship which we talked about in the previous module. Okay. So in this relationship, this is the wave function for unperturbed system psi n naught, this is the wave function for an unperturbed system psi n naught, and this is the energy for unperturbed system En naught. Okay, and this is your Hamiltonian for unperturbed system. This psi n1 is the correction to the wave function, first order correction to the wave function, and this H prime is the perturbation. So what we will do, we will replace this two psi n naught and psi n naught by this linear combination of the wave function psi n naught and psi L naught. Okay, so what do you get? Replacing psi n naught by linear combination gives, if you have this equation, then it gives you this one. So what I did here, it is psi n naught, psi n1, H naught, En naught, that's there. Then you have En1, and instead of psi n naught, you write Cn psi n naught, Cl psi L naught, a linear combination. Then minus H prime, Cn psi n naught, Cl psi L naught. That I can write, because the only change, this relationship we used in the non-degenerate perturbation theory also. From this relationship we got En1 is equal to integral of psi n naught H prime psi n naught theta. Okay, same perturbation relationship, first order perturbation relationship we are using here also, but the only change which we are making is that for this particular example we have taken that En naught is twofold degenerate, and it has two different wave functions, psi n, which is represented by psi n naught and psi L naught if it is twofold degenerate, and Cn and Cl is the coefficients which tells you that what is the contribution of psi n naught and psi L naught to the actual wave functions. Okay, so we replaced the unperturbed wave function by a linear combination. That's what in simple terms we did, nothing else. Okay, so this equation was already there with you in the non-degenerate perturbation theory. The only thing is that we have taken twofold degenerate state of En naught, and the total wave function what we are using is a linear combination of the individual wave functions. Okay, it's simple rearrangement. H prime psi n naught from the RHS I have taken as in the LHS, and then we have this relationship H naught psi n1. So this relationship H naught psi n1 and En naught psi n1 from minus En naught psi n1 on LHS, it comes to the right hand side and it becomes En naught psi n1, and rest of the thing is same. Okay, so it's simple rearrangement. This comes here. Okay, this comes here and this comes here. So that's simple as this. Simple rearrangement of the above equation, which gives you this one. We say it equation number 1 for reference. Okay, now what we do, we multiply from the left by psi n naught and integrate over whole space. If you do this multiplication, then keep it in mind, the constant term you will bring outside, and then you will write this psi n naught, new psi n naught with which you are multiplying on the left hand side. So if you do that integration, what do you get? For the first term, what you will get? Cn is a constant, so Cn outside the integration. Then psi n naught you are multiplying, so psi n naught. Then this H prime will come, and again this psi n naught is there. So the first term will be Cn integral of psi n naught H prime psi n naught theta. If you have second term, then second term Cl is a constant, so it will be outside. Then the integral then the wave function with which you are multiplying psi n naught, so it is psi n naught. All this is the wave functions which you are multiplying with psi n naught. Then here you have psi n naught, Cl is a constant, so outside, and H prime has to be there, so H prime and psi L naught theta. Okay, then again this wave function is the wave function with which you are multiplying to which? This one, H naught psi n1, so H naught psi n1 theta. On the right hand side, you have En1 and Cn. So bring En1 and Cn outside, and then this is the wave function which you are applying from the left side, multiplying from the left side and integrating. So this wave function was already there, psi n naught theta. Then you have Cl and En1. This En1 multiplication, so Cl En1, and again this is the wave function with which you are multiplying, psi n naught, psi l naught theta. Then En naught, okay, En naught, psi n naught, psi n1 theta. It's psi n naught, psi n. All these psi n naught with which you are multiplying from left. Okay, that you remember. All integral it is on the left hand side, psi n naught, psi n naught, psi n naught. Now what happens to this integral? Look at this. The first integral remains as such, Cn psi n naught h prime psi n naught theta. Second integral, Cl psi n naught h prime psi n naught theta as such, no issue. Third integral, psi n naught h naught psi n1 theta, no change. So left hand side doesn't change. On the right hand side, what you find is that you have En1 Cn1 and psi n naught theta. So this is your normalization condition. Okay, the same wave functions. So it becomes Cn En1. So this becomes equal to 1. Okay. Now on the right hand side, the second integral is psi n naught, psi l naught, two different quantum state. So this will be equal to 0. So this term will go. Now in the third term, you have En naught and psi n naught, psi n1 theta. Okay. So we have one term omitted from the right hand side, and the first term on the right hand side becomes equal to Cn En1 because of the normalization condition. Okay. If you further solve this, write this integral, it's the same integral, then since H naught is a Hermitian operator, H naught is a Hamiltonian for unperturbed system. So if it's a Hamiltonian for unperturbed system, it will be a Hermitian operator. I said we talked about Hermitian operator in details when I was talking about the quantum mechanical postulates. Okay. So what does this Hermitian operator means? You change the wave functions from 1 to 3 and 3 to 1. Okay. So this is your Hermitian condition, that psi n naught h naught psi n1 theta will become psi n naught h naught psi n naught theta. No complex conjugate I have written because it's all real functions. Okay. So if you write this one, then you see here you are operating with an Hamiltonian on psi n naught. So what you can write? It's the Schrodinger wave equation. So it will be equal to En naught psi n naught, and then En you can bring outside. So you can write En naught outside and then psi n1 psi n naught theta. And if you use this particular equation, psi n naught h prime psi n1 theta, then you look at this equation. This is the same integral as this one, psi n naught h prime psi n1 theta. Okay. And if in place of this you write this equation, En naught psi n1 psi n naught theta, then it is the same thing here, En naught psi n1 theta. So on the left hand side also, on the right hand side also, you have the same integral. Okay. So it will go, and ultimately, so these two will go in the red. This will go and this will go. So what you have is this one, Cn psi n naught h prime psi n naught theta minus Cn En1. So this Cn En1 I have brought on the left hand side, so it is minus Cn En1 plus Cl plus this Cl psi n naught h prime psi l naught theta is equal to 0. Okay. So now what you can do is you can rearrange this. See, this here Cn is the coefficients, here also Cn is the coefficients, but here you have Cl as the coefficients. So the terms of the term with the Cn you will combine together, and the term with Cl as the coefficient you combine together and write the integral in a different form. Like write this integral, the first integral as h n n prime, then minus Cn1 you can write. Cn h, this integral I have written as h n n prime. Okay. So it will be Cn h n n prime minus En1, then plus Cl h n l prime. This integral again with the same will be h n l prime is equal to 0. Okay. So we got this equation. We did nothing. We used the first order perturbation equation And the only thing which we did is that instead of using psi n naught as the wave function for perturbed system, we have taken a linear combination of two eigenfunctions which corresponds to the same energy in place of psi n naught. That's all. And then we multiplied with psi n naught and integrated over whole space, and we got this relationship. But when I multiplied with psi n naught, I said you multiply it from the left hand side. What will happen if you multiply it from the right hand side? You will get a similar equation. Multiplication from right by psi n naught in equation 1 and integrating over whole space will give you a similar equation, but the coefficients will be different. Now here the coefficients of Cn will be h prime ln. It's nl, it's ln. Okay, so the sequence changes, and then you have the sequence, the coefficient Cl will have value hll prime minus en1 prime. Okay, so this is nn, this is ll. It means you have two different values, two different coefficients Cn and Cl, and for these two you have two simultaneous equations. So the coefficients could be written as a determinant and equated to 0. Okay, so what is the determinant? Two simultaneous equation with two coefficients, so it can be written as the determinant, and the determinant is this one, hnn prime minus en1 hnl prime, and then the next row hln prime hll prime minus en1. Okay, so if you solve this determinant, you can get the value of en1. So this is called secular equation, and this we have done in your variation treatment also, secular equations. Okay, as two solutions. So if this is the determinant, we can solve this determinant, and if you solve this determinant, this should be the value, hnn prime minus en1 multiplied by hll prime minus en1 minus hln prime into hnl prime. Okay, and if you solve it, finally what you get is a quadratic equation, en1 is square, then en1, and this is your C value. Okay, so what you get is E plus minus you get, and with this plus minus term, two different values of energy you get. Thus the corrected energies are E, if you add to the unperturbed energy En naught, first one of the square root, that is plus value En plus, you will get this as the system of energy of the perturbed system, and if you add En minus naught, then you get the another value of energy for the perturbed system. It means what happens after perturbation, the degeneracy is lifted, because En plus naught and En minus naught may not be same, but it may be same also. In which case it will not be same, it will be same that I have written. Both these energies will be real, since the diagonal matrix element Hn prime and Hnl prime of the Hermitian operator H are real. So real energy values you get. If these integral Hn prime and Hll prime are equal and H prime Nl is 0, then what you get is En plus is equal to En minus. What does it mean? It means that En value, which is summation of En naught plus En plus and one I have to write first order perturbation, En naught plus En minus 1. Okay, so these two energies are same because it is a degenerate system, and the correction also is same. So what do you mean? These two values will also be same, and the energy of the perturbed system will also have degenerate energy level. For a two-fold degeneracy we have talked about. It could be more also, but for the simplification I just wanted to tell you the theory behind the degenerate perturbation results. So the degenerate perturbation theory for a two-fold degenerate system we did, and we got the correction to the energy En plus and En minus, and I said you that there is a condition in which both these values En plus and En minus will be equal, and the perturbation and the system degeneracy will not be lifted. Okay, so these two are broadly the theory of perturbation for time independent system. We have not talked about the time variable till now. For a degenerate system, for a non-degenerate system, time was not variable. So time independent perturbation theory is of two types. One is non-degenerate perturbation and another is degenerate perturbation. So both these theories we talked about. Now what we have not talked about is that what happens if the time comes into picture, and what is the significance of time dependent perturbation theory? Why should one do the time dependent perturbation theory? And this will be the topic which I will cover in the next module. Okay, thank you.